Welcome to the deep dive. Today, we're looking into some, pretty significant reports about a large hidden underground facility in Iran.
Right, and the big speculation is that it might be for tritium extraction, potentially for nuclear weapons.
Exactly. So, our mission for you in this deep dive is pretty clear. We want to understand why tritium is such a big deal in the nuclear world.
And get a sense of what Iran might actually be capable of doing, what challenges they face, and they are significant challenges.
And of course, the wider implications, what this all means globally.
And we're drawing heavily today on the work of Dr. Lev Neymotin, specifically his paper, Tritium Trap, Iran's nuclear aspirations, but also looking at his wider background.
Okay, so let's jump right in. There's some language used in reporting this that can be, a bit misleading, isn't there?
Yes, definitely. You often hear tritium described as, enhancing nuclear weapons.
Like it's just a minor boost or something.
Yeah, exactly. But that really, really undersells its importance. Here's the thing you need to grasp. Tritium isn't just a booster. It's the key ingredient that transforms a basic fission bomb.
Like Hiroshima and Nagasaki.
Right. Into a full-blown thermonuclear weapon, a T-bomb. It's less an enhancement, more like, the difference between dynamite and a nuke in the first place is that fundamental shift.
Okay, that puts it in perspective. So we are talking about a completely different scale of destructive power. Can you maybe give us some numbers to illustrate that?
Sure. So the Hiroshima bomb, uranium, was about 15 kilotons. Nagasaki plutonium, around 21 kilotons.
Okay.
Now, you can use a tiny bit of tritium gas to make the fission part burn more efficiently. That's called boosting. A boosted fission bomb might get you up to, say, 50 to maybe 300 kilotons, still fission, just more powerful.
Right.
But a true thermonuclear weapon, we're talking potentially 1 megaton up to 50 megatons or even more. It's a quantum leap.
A quantum leap. So not just tactical anymore, but truly strategic global impact weapons.
Absolutely. Without tritium, any nuclear capability Iran might develop would likely be stuck in that lower fission yield category. Tritium is what unlocks that thermonuclear door.
Okay, crystal clear. So if Iran is pursuing this, how would they likely go about producing tritium given their known nuclear facilities?
Well, based on Dr. Neymotin's analysis, there are really two main routes that seem plausible given their existing infrastructure.
Okay, what's the first?
The first involves their heavy water reactor, the Arak IR-40. The interesting thing here is that even when it's running at low power, neutrons bouncing around interact with the deuterium in the heavy water itself.
And that makes tritium, just as a byproduct.
Sort of, yeah. A natural consequence of using heavy water. But, and this is a big but, the amount produced is estimated to be pretty small, maybe 20 to 100 curies a year baseline.
That doesn't sound like much.
It's not. And then you have the problem of getting it out of the heavy water. You need highly sophisticated separation tech things, like isotopic distillation columns or thermal diffusion. Think huge, complex facilities like Canada's Darlington plant, which does this. It's serious engineering.
Okay, complex and low yield. What's the other option?
The other main path is to irradiate lithium targets, specifically lithium-6, with neutrons.
How does that work?
Basically, you take lithium-6, often in a ceramic or metal form, put it in a neutron field, maybe from a research reactor or an accelerator, and when the lithium-6 absorbs a neutron, it splits into tritium and helium.
Okay, so you need a neutron source for that.
You do. And then, after you've irradiated it, you have to get the tritium out of the lithium material. That usually involves high temperatures, maybe heating it in a vacuum or flushing it with helium gas. Again, not simple stuff.
Right. Both sound challenging. But let's talk scale again. How much tritium do you actually need for one of these thermonuclear weapons?
Now this is where the challenge really becomes apparent. Neymotin estimates a single thermonuclear warhead needs about 3 to 5 grams of tritium per year.
Per year. Why per year?
Because tritium is radioactive, it decays. It has a half-life of about 12.3 years. So just to keep the weapon at its designed yield, you constantly need to replenish the tritium that's decaying away.
Okay, 3 to 5 grams a year. How much radioactivity is that?
Well, 1 gram of tritium is roughly 9,600 curies. So for just one warhead, you're looking at needing something like 30,000 to 50,000 curies of tritium production every single year.
Wait, okay. You said that a Iraq reactor might produce 20 to 100 curies a year.
Exactly.
That's a massive shortfall. Orders of magnitude.
2 to 3 orders of magnitude, yeah. So to bridge that enormous gap, Iran would need reactors running at much, much higher power levels, or they'd need industrial-scale production of lithium targets, plus large, very complex, and currently undetected extraction and purification plants.
So, finding a new underground facility, while concerning, doesn't automatically mean they're anywhere near having the tritium for T-bombs. The scale required is just vast.
It is. And producing the tritium is only part one of the problem. Yeah. Part two is actually building the weapon itself.
Then that's harder, too.
Oh, exponentially harder than a simple fission bomb.
Okay, let's dive into that. What makes them so much more difficult to engineer?
Several key things. First, the primary fission part of a T-bomb needs an extremely precise, perfectly spherical implosion to get the conditions right for the secondary fusion stage. Much more precision than a basic fission device.
Okay, precision implosion. What else?
Second, you have to inject the tritium gas into the weapon's core at exactly the right moment. We're talking timing measured in microseconds, millionths of a second, just before it detonates.
Microseconds.
And third, you need a network of very specialized detonators, like exploding bridge wire detonators, and they all have to fire at precisely the same instant across the implosion sphere. Tolerances there are down to picoseconds, trillionths of a second.
That level of precision is, well, it's hard to even imagine.
It's extraordinarily demanding engineering. A slightly uneven implosion might still work for a basic fission bomb, maybe just lower yield. But in a thermonuclear weapon, any asymmetry, any timing error, and you likely get a drastically reduced yield, or just doesn't work at all.
So when we've heard concerns about countries trying to get certain types of detonators...
It's often these ultra-precise systems they're worried about, the kind needed for thermonuclear designs. And look at history, even established nuclear states like India and Pakistan. They had fission bombs for years before they successfully managed to test the thermonuclear device. It's a huge jump.
That history really underscores the difficulty. So how do you even know if one of these incredibly complex devices would work? Can't you just simulate it on a supercomputer?
That's a really critical point. For thermonuclear weapons, the answer is largely no. You can't just rely on computer models. The physics of the fusion burn are just too complex, too chaotic and nonlinear. You can model parts, but getting the whole dynamic right in simulation is pretty much impossible with current tech. You absolutely need real-world physical testing.
Actual nuclear tests.
Yes. To confirm things like the timing of the fusion fuel injection, how the radiation flows from the primary to compress the secondary, the symmetry of the whole implosion, all these interacting parts.
So has any country ever deployed a T-bomb without testing it first?
No. No nation has deployed a new thermonuclear design without physical testing. It's considered essential for reliability.
But testing has downsides, right? You use up precious tritium.
You do. And of course, there's the huge risk of international detection and the massive political fallout that would follow. So deploying an untested T-bomb, that would be an enormous strategic gamble. Hugely unreliable.
It just seems like obstacle after obstacle for Iran here. Which brings us to another big one, the cost. You mentioned Neymotin's argument about nuclear weapons being an economic liability.
Yes, he makes a strong case, particularly in his paper, Nuclear Weapons, Asset or Liability. Maintaining any nuclear arsenal is incredibly expensive, but thermonuclear weapons, especially with the tritium requirements, are significantly more so.
And Iran's economy isn't exactly booming.
No, it's under severe strain from sanctions, unemployment, lack of investment. And remember that 12.3-year half-life for tritium. That means you need constant production just to tread water, plus ongoing maintenance and refurbishment of the warheads themselves.
It's not a one-off cost then, it's a permanent budget line item.
A very large one. Neymotin estimates that scaling up tritium production alone could cost Iran something like $200 million to $400 million per year.
Wow.
And that's just production. Add in secure storage, specialized labs, trained personnel, maybe testing infrastructure. The costs become enormous. It would inevitably divert scarce resources from critical needs, healthcare, infrastructure, education in an economy that's already stretched thin.
So his argument is that for a country like Iran, these weapons are actually a trap, a tritium trap, as the paper title suggests.
Pretty much. They might look like an asset, like they bring prestige or power, but the ongoing technical and economic burden makes them a huge liability, potentially undermining the country's stability in the long run. Its prestige at a potentially crippling price.
Okay, and just to circle back to the source of this analysis, Dr. Neymotin himself, his background seems particularly relevant here.
Oh, absolutely. His resume really speaks volumes. He has a PhD in mechanical engineering, spent almost 20 years at Brookhaven National Lab.
Doing what exactly?
A lot of work on nuclear reactor safety, accident analysis. But crucially, he was deeply involved in international nuclear security programs. Specifically, helping implement better material control and accounting MC&A systems at Russian nuclear facilities, including weapons sites, as part of U.S.-Russian cooperation.
So he has direct, hands-on experience with how nuclear materials are tracked and secured in a weapons context.
Precisely. He understands the practicalities, the vulnerabilities, the real-world challenges, and even before Brookhaven, his early career in Russia involved research into thermonuclear power and related physics.
So he has both the fundamental physics background and the practical nuclear security experience.
Right. Plus, numerous publications on reactor safety, codes, Chernobyl analysis, VVER reactors. It's a very deep and broad expertise that makes his perspective on Iran's potential path extremely credible and insightful.
Okay, so let's try to summarize this deep dive. Tritium. It's not just an enhancement, it's the absolute key to thermonuclear weapons and that massive leap in destructive power.
Check. And while Iran might have pathways to produce some tritium, getting the vast quantities needed for an arsenal faces enormous technical and resource hurdles.
Right. And actually building and importantly verifying these weapons is exponentially harder and more expensive than fission bombs. It requires physical testing.
And untested T-bombs are inherently unreliable, making them a massive strategic gamble. Plus, the ongoing economic drain is huge.
So it leaves us with a really big question for you, the listener. If these reports about Iran pursuing tritium are accurate, given all these immense challenges, the technical difficulty, the cost, the need for testing, what could their real strategic intention be?
Is it a genuine, albeit incredibly difficult, push for thermonuclear weapons? Is it a complex bargaining chip for negotiations? Or is there another strategic calculation we're not seeing?
It definitely gives you a lot to think about, doesn't it?
It certainly does, and it underscores why continued vigilance and critical analysis are so important when looking at these kinds of developments. We hope you'll keep exploring and thinking about these complex issues.